So in this video, we're going to go over the three main types of formalisms for making measurements in quantum mechanics. So we'll start with the general measurement formalism. So the way this works is you define a collection of measurement operators, each one corresponding to a particular measurement outcome, which we'll denote by little m. And if we have some state vector living in a Hilbert space, like psi here, then what these measurement operators are just linear operators on that Hilbert space. But we also enforce the constraint that if we sum over all little m and we take the Hermitian conjugate times itself for each of these corresponding measurement operators, that this should sum to the identity. And the reason for this is because the way we denote probability, or the way we define probability here, is the expectation value of that measurement operator having acted on our state. So what this is saying is essentially these probabilities should add to 1, which adds up. And the general measurement formalism actually allows us to go a bit further and have some way to define the state after a measurement. So the state after making a measurement, let's say we obtain some little m measurement outcome, then the state that we're left with, which we'll call psi sub m, is equal to that measurement operator acting on whatever state we started with over the square root of this expectation value, which is just the probability of having obtained that measurement outcome. And this is nice, but for our purposes and most purposes in quantum computing and quantum mechanics, we are not very concerned with the state after a measurement. So this leads us into the POVMs. So POVM stand for positive operator valued measure, and the actual technical details of the name is not really that important, but essentially what it is a mathematical convenience. So it's actually identical to the general measurement formalism, but set up in a way where we don't really care about talking about the state after a measurement. So now we can describe what a POVM is. A POVM is essentially, instead of referring to these measurement operators like this, we are going to instead define a new type of operator, E sub m, which is going to be what we had previously, but the Hermitian conjugates times themselves. And what this does for us is it turns these E sub m's into Hermitian operators and just cleans up things a little. So now if we go over our constraints again, they are exactly the same. These should sum to the identity. And now the probability of any measurement outcome is just this. So that's what a POVM is. It's very simple. It's just like what we had before, but just cleaning things up a little. And now you can see, like, it might be kind of annoying to talk about the state after measurement again, because we'd have to like extract just one of these components from E sub m. So this is like intended so that we're not really worried about that. And this leads me into the third and final measurement formalism, which is just a subset of general and POVMs, and that is projective valued measures. So this is where our POVM operators are actually projections. And not only that, but they're orthogonal projections. So now instead of just saying E sub m, we'll say P sub m. And projectors have the property that they square to themselves. So now, again, our constraints are the same thing. They sum to the identity. The probability is the same. But now we have this third and final constraint, which is that these are orthogonal projectors. So P sub m prime times P sub m is the Kronecker delta of m prime and m times P sub m. Now, one way to see why these are going to be orthogonal projections is because what they're going to do is take a quantum state and project it onto the subspace spanned by one of the basis vectors in some orthonormal basis. So, for example, if we have just a single qubit, we know that there's an orthonormal basis for the computational basis, so that would be 0 and 1. And then in this case, for our PVM, we can take the orthogonal projections onto these basis vectors. So we'll have 0 and 1. And now any single qubit state can be represented as a linear combination of these basis vectors. So if we have some single qubit psi, we can put into this linear combination alpha times the 0 state plus beta times the 1 state. And now if we wanted to know with these PVMs, what's the probability that we measure 0? Then we just apply our rules from above, and this is going to be the expectation value of having applied this projector onto the state. And it's pretty easy to see that this is just going to give us the complex conjugate of alpha, the amplitude over 0, times alpha. And this is just the magnitude squared of alpha, which is actually just Born's rule, which relates amplitudes to measurement statistics. And then likewise for measuring 1, it's going to be the amplitude squared for that coefficient. So this is just a simple example. And it's kind of nice to see these PVMs in action. They're very easy to work with, and things are a lot cleaner than the general measurements in POVMs. So in our study of non-local games in particular, we're actually only going to need to consider PVMs for this very nice theorem called a Neymark's theorem. And what this theorem says essentially is that any POVM can be realized as a PVM simply by extending our Hilbert space. So any POVM can be realized as a PVM by extending Hilbert space. So if we have some Hilbert space and we have a POVM defined for this Hilbert space, we can turn that POVM into a PVM by adding some ancilla system. And that's roughly what this theorem tells us. And for this reason, we'll be able, for our purposes, we'll be able to only look at PVMs, and it'll just make things nicer for us.